Good morning. This is the math department at Amjad High School for grade 11. This is the first session on permutations. The objectives of this session will study the fundamental counting principle, the concept of permutations of n distinct objects, permutations of r distinct objects out of n, finally, permutation with repetition of r objects out of n. Fundamental counting principle. Let's start with an activity. Assume Sammy has 4 shirts and 2 pants. List all the possible outfits that Sammy has. To list the possible outfits, we can say that he can have this yellow shirt with that pant, this shirt with that pant, this shirt with that pant. The best way to list all the possible cases is to find an organized way so that we don't miss any of the options. That's why we're going to use what we call a tree diagram. Tree is nothing but an organized way to list all the possible outcomes. Let's look at the tree diagram. First, the shirts are S1, S2, S3, and S4, or we can refer by color or whatever. Name the pants P1 and P2. Now, this is the tree diagram. First, Tammy has to choose a shirt, either S1 or S2 or S3 or S4. In case he chose S1, what about the pants? It could be pant P1 or P2. If shirt 2 is chosen, then he can go to the pant, either P1 or P2, and so on. So one of the possible outfits is S1 P1. Another one is S1 P2. Another one is S2 P1, and so on. So the tree diagram is nothing but listing all the possible cases, but in an organized way, so that we do not repeat the same outcome twice, or we don't miss any of the possible outcomes. So the possible outfits are S1 P1, S1 P2, and so on. So these are all the possible outcomes. This shirt with that pant, this shirt with that pant, and so on. How many outcomes are there? We notice that the number of possible outfits is 8. Can we find this number without listing? Because we can expect that sometimes the number of shirts could be much more than this, or the number of pants is much more than this. Then is it logical to list all the possible cases? Is it practical to do this? So we need to find a general method to find the number of outfits without actually listing them. This is what we call the fundamental counting principle. It says if an experiment A can be done in m ways and another experiment B can be done in n ways, then both experiments A and B can be done in m times n ways. Or in other words, we can say that if an experiment is composed of 2 or even 3 components, if the first component can be done in m ways, a component could be the shirt. Another component is the pant. So if it can occur in n ways, you may have a third component, like a hat or whatever. Then to know the total number of ways, you can simply multiply the number of each possibility. So we can say in the previous activity that the number of possibilities to get a shirt is 4, and the number of possibilities to get a pant is 2, and the outfit in this activity consists of a shirt and a pant, and consequently, if you want to know the total number of outfits, you simply multiply 4 times 2, and this will be 8, as we have seen in the tree diagram. Application 1. Assume that you have 3 distinct pens, 5 distinct pencils, and 4 distinct books. Not any of the two items are the same. So every item is different from the other. In how many ways can we choose one pen, one pencil, and one book? So the experiment here has three components. The first component is a pen. The second component is a pencil. And the third component is a book. Shall we list all the possible cases? It could be a very huge number and we will waste our time. Since the number of ways to choose a pen is 3, and the number of ways to choose a pencil is 5, and the number of ways to choose a book is 4, then by the fundamental counting principle, 3 times 5 times 4, which is 60, will give you the total number of selections of 3 items of these 3 sets. Application 2. In a restaurant, a meal is made up of salad, a main course, and a dessert. The menu offers 3 salads, 8 main courses, and 5 desserts. How many different meals can we form? The number of ways to choose a salad is 3. The number of ways to choose a main course is 8. And the number of ways to choose a dessert is 5. So the total number of meals that you can form using the fundamental counting principle is 3 times 8 times 5, and that's 120. Before we proceed to another concept, we need to introduce you to a mathematical notation. It's just a notation and not a concept. It's called factorial, so it's just a notation. Consider the natural number n, 0, 1, 2, 3, whatever. We call n factorial denoted by n factorial, like this exclamation mark. And this is found there on your calculators. We'll see this in the next session. The natural number, which is defined by 1 times 2 times 3 times 4 times up till n, is denoted by n factorial. Again, this is not a concept, just a notation. For example, what does 3 factorial mean? It means 1 times 2 up till 3. So 1 times 2 times 3, which is 6. What does 5 factorial mean? It's 1 times 2 times 3 times 4 times 5, which is 120. Again, 5 factorial can be done using your calculator because factorial notation is found there as the radical is there. Can we say minus 3 all factorial? Nonsense, because we're talking about a natural number. Can we talk about 3.2 like a decimal number factorial? Again, here this is nonsense. Factorial is just used for positive natural number, like 7 factorial. It's 1 times 2 times up till 7. For example, if I want to simplify this without the use of calculator, what does 8 factorial over 6 factorial means? If you think about it, 8 factorial is 1 times 2 up till 8. So from 1 till 6 is 6 factorial. It can be cancelled out with the 6 factorial in the denominator. So you will be left with 8 times 7, which is 56. What about the 12 times 11 factorial? Can you simplify it and to be written as 1 factorial? 11 factorial actually means 11 times 10 times 9 times 8 up till 1 or down till 1. But you're multiplying by 12. So actually this is from 1 till 12, which is 12 factorial. By convention, only by convention as a notation, 0 factorial is considered to be 1. You can check this on your calculator. Application. Without using the calculator, calculate the following. 10 factorial over 8 factorial. For sure, 10 factorial means 10 times 9 times 8 times 7 times 6 and so on. But what about 10 times 9? When you reach to 8, stop, because 8 and down till 1 is there, 8 factorial. So they can cancel out. So you will be left with 10 times 9, because 10 factorial is 10. I'm moving here backward. 10 factorial, you can say it's 1 times 2 up till 10, or you can say it's 10 times 9 times 8 down till 1. So 10 factorial is 10, go one step down, 9, then 8 till 1 is nothing but 8 factorial, and it's better to write it like this so that it can be cancelled out with the 8 factorial in the denominator. So you will be left with 10 times 9, which is 9. What about 8 factorial times 5 factorial? 8 factorial is 8 times 7 times 6 times 5 factorial. Why I'm saying 5 factorial? Because 5 factorial is there. You can cancel it out. 5 factorial, keep it like this, whereas 3 factorial, calculate it. It's 1 times 2 times 3, which is 6. Now, this 5 factorial will cancel out with this 5 factorial. And this 6 will cancel out with this 6. You will be left with 8 times 7, which is 56. Now, let's move to the new concept now, or another concept in this session, permutation with n distinct objects. What do we mean by permutation? Permutation is also called arrangement. We call a permutation of n elements every arrangement or ordered arrangements of these n elements. When we talk about order, this means that A followed by B is different from B followed by A. Let's see an activity to illustrate what we mean by this. List all the words of 3 distinct letters that can be formed out of the letters A, C, T. Again here, if you think about it, you can simply list ACT, ATC, CAT, CTA. It's easy to list them because these are only 3 letters. Or you can use a tree diagram to make sure that you are listing without repetition or without missing. Or you can even use the fundamental counting principle. You can draw 3 boxes and you think about the number of options for the first letter, then the second letter, then the third letter. But we want to make this a formula because this is a very standard situation where you have like 5 letters and you want to permute them all. You have here 3 letters and you want to permute them all without repetition. You can list them: ACT, ATC, CAT, CTA, TCA, TAC. So how many? 6. Notice that the 3 letters can be arranged by 6 ways, which is actually 3 factorial, which is 1 times 2 times 3. Can we generalize? Can we expect the property of arranging n distinct objects? So assume instead of 3 letters, you have 10 letters. For sure, we cannot list them. This will be a very huge number. So simply, you don't need to list them to know the number. The number of arranging 10 letters will be 10 factorial. So, as a conclusion, the number of permutations of the distinct elements of a set consisting of n, so the number of permutations of n distinct elements is n factorial. Application 1, how many 4 distinct digit numbers can be formed using the digits of the set 2, 5, 6, 8? So let's say 2, 5, 6, 8 is a number, 4-digit number. But what about 5, 2, 6, 8? What about 8, 6, 5, 2? What about 8, 5, 2, 6? Can we list all? We don't need. You're just permuting, arranging 4 distinct letters or numbers. So no need to list them all. You can say that it represents the number of permutations of 4 distinct digits, and consequently you will get 4 factorial, which is 24 possible outcomes. So without actually listing all the outcomes, you can find the total number. Application 2. In how many ways can 3 students, Sami, Farid, and Zahi, be seated on 3 chairs in a row? So Sami can be here, Farid can be here, Zahi can be there, or Zahi can be here, Farid can be here, Sami can be there. Do we need to list all the cases? The possible outcomes are these, if we want to list. But for sure, I'm just giving you the answer, but if you have this in an exam or whatever, in any situation, you don't need actually to list the cases. You can tell that the different number of ways you can let these students sit on these three distinct chairs. It will be 3 factorial, which is 6 ways, and here the 6 ways are. Now, what about permutation of R distinct objects out of N? Consider the set E, A, B, C, D. You have to be careful here. Here we're not arranging the 4 numbers. How many 2-letter passwords can be formed from the elements of E if repetition is not allowed? So actually you have 4 numbers, but not like in the previous case. We're not arranging these 4. We want to form a code of 2 letters out of these 4 letters. So you are choosing 2, then permuting them. Like for say, let's say AB, BA, AC, CD, DB. Again, we are not permuting 4 letters. We are permuting 2 out of 4. By the way, for sure, when we say password, I mean order is important, which means that the code AB is different from the code BA. We can list the codes. The first letter, this is fundamental counting principle, by the way. So the first letter has 4 options. What about the second option? The second option will be 3 options because the first letter is not allowed to be repeated. In this way, actually, we are listing. You will ask me that each time we ask you about code or codes, you have to list them. No, we're just explaining. We're just convincing you that these are the codes A, B, A, C, A, D, B, A, B, C, and so on. So the possible codes are these. How many, by the way? 12. You should have expected this using the fundamental counting principle because the first letter has 4 options, whereas the second letter has 3 options because repetition is not allowed. So 4 times 3 is 12. But again, this is a standard situation where you are permuting R elements out of N elements. You don't need to list. You don't even to use the fundamental counting principle. You should find a regular formula that you have to use. So in general, consider this, again, we're repeating the question. It represents the number of permutation of 2 distinct elements out of 4. We notice that actually 12 here can be seen as 4 factorial over 4 minus 2, where 4 is representing the total number of elements, and 2 here represent the number of elements that you are permuting. As a conclusion, this has its own formula, and it's found there on your calculator. This notation, P, R, N, it's read as permuting R out of N, or permutation of R elements out of N. It has a formula, N factorial over N minus R factorial. In this case, R should be less than or equal to N. For sure, you cannot permute 5 elements out of 2. You permute 2 out of 5, or 5 out of 5. So the answer here, which is 12, it can be seen as permuting 2 out of 4. This notation may be used, and it's found there on the calculator. Some other students sometimes they use different methods like listing, like using the fundamental counting principle. It's fine, it's okay. But you have to know this notation because it's found there on your calculator, and sometimes you are asked to deal with it. So this is R and this is N, permutation of 2 out of 4. So in general, the number of permutation of R distinct objects out of N is PRN, N factorial over N minus R factorial. Application 1, actually you don't need to work on this because P 3 out of 7, for example, it's just used on calculator. You find it using calculator. You don't need to perform these by yourself. But as a formula, we are telling you that this is the formula. For security reasons, the lodgers of a building decide to equip the main entrance door with a security numerical code composed of 4 digits. What is the number of possible codes they have or they can form if repetition of digits is not allowed. This is very important when I tell you if repetition is allowed or repetition is not allowed. If repetition is allowed, like the code could be 9955, this is a different situation. We're talking, as you know, how many digits you have in general? You have 10 digits because the digits are 0, 1, 2, up to 9. What are you doing actually? If I want to list like one code could be 6540. We cannot say 6554. Repetition is not allowed. 6540 is a code, but 6045 is a different code. So actually, what are we doing? Actually, we are permuting, we are arranging 4 out of 10. So the number of possible codes is simply permuting 4 out of 10. If you want to find the answer, you don't need to write any factorial notation. You can use your calculator. I'm writing this here in the session, but actually, you don't need to use it. You go to your calculator, you can check it now, and in the second session, we will teach you how to use your calculator. It's only one button that you have to press, and you will get the answer directly. It's 5040. Another application, how many 4 distinct digit numbers can be formed using only the odd digits? Since you are permuting, arranging 4 objects out of 5 objects, so the answer should be exactly permuting 4 out of 5, which is directly using calculator 120. Another example, in how many ways can 5 copies of different objects be placed in 8 distinct boxes so that 1 copy is placed in a box? If you think in this situation, actually you are permuting, arranging 5 out of 8. So the answer will be directly permuting 5 out of 8. And the answer using calculator, so again, I'm telling you that you don't need to write this. But if you don't have a calculator, you need to write it. So the answer using calculator will be directly 6720. Now, permutation with repetition of R objects out of N. Consider the set A, B, C, D. How many 2-letter passwords can we form from the elements of E if repetition is allowed? So we cannot say here that we are permuting 2 out of 4. Permuting 2 out of 4 means these are distinct elements and repetition is not allowed. So here you are forming a code where repetition is allowed. Actually, this is called a to-list. So the number of options for the first letter is 4. But the number of options for the second letter is also 4 because repetition is allowed. So by the fundamental counting principle, you can see that you have 4 times 4, 16 options. So actually, you don't need to list. We're just listing this because we're explaining the chapter for you. Consider the set ABCD again. How many 2-letter possible words? So we can say that the number of possibilities is 16. 16 actually is 4 to the power 2. So whenever you have a similar situation, the number of permutations with repetition of R objects out of N is always N to the R. Again, I'm telling you, you don't need to use this particular formula. You can think about the situation starting from fundamental counting principle by thinking of the number of options for the first step, the number of options for the next step, or whatever, then you multiply them all. But if you can match the situation with one of the general cases, you can give the answer direct. So the number of permutations of repetition of R objects out of N is N to the R. This is called R list. A coin is tossed 3 times. Find the number of all possible outcomes. You can think of this because repetition is allowed. If you flip a coin like 3 times, you can get a head on the first toss, but another head on the second or on the third or whatever. So actually here you can think of it by using this method, because repetition is allowed. You are doing 3 steps and each step has 2 options. So it represents the number of permutation with repetition of 3 elements out of 2. So the number will be 2 power 3, which is what? 8. Actually, you can solve this same problem as I have said, using the fundamental counting principle. How? By saying that I'm flipping a coin. So I have a first outcome, second outcome, and third outcome to form all in all the outcome of the experiment. What about the first toss? You may have the number of choices for the first box is 2. What about the number of options for the next box? Here again, you are flipping the coin. You may get a head or a tail, regardless of the results of the first flip. So the number of choices for the second box is 2. And now the number of choices for the third box will be also 2. Consequently, by the fundamental counting principle, the number will be 2 times 2 times 2, which is 8. I prefer you use this method in this situation. Another application, a die is rolled twice. Find the number of all possible outcomes. When we talk about a die, we are talking about a fair 6-sided die, the regular one, 1, 2, 3, 4, up to 6. So if you think about it, the first die may have 6 options. What about the next one? 6 options, and repetition here is allowed for sure. You can get 4 on the first die and another 4 on the second die. So the number of options will be 6 power 2, which is 36. Or you can think about it by using the fundamental counting principle by drawing 2 boxes. The number of options for the first box is 6, and the number of options for the next box will be also 6. So 6 times 6 will be 36. In how many ways can a student answer 10 multiple choice questions, 10 true or false questions, if he should answer all these questions? So think about it. So the first option, the first box, 2 options. The second box, 2 options. Repetition here is allowed. So it will be 2 power 10. Or you have to draw 10 boxes and giving each box the number of ways it can be chosen. So the answer will be 10, 24. As a conclusion, if you are permuting n distinct objects, if you have, let's say, 5 letters and you are considering all the permutations of these, in how many ways can this be done? Do you need to think of fundamental counting principle or draw boxes? You can, but it's a very easy situation. You are permuting 5 distinct objects, so simply that's 5 factorial, n factorial. If you are permuting r out of n, if you have 6 letters but you are choosing 3 to arrange them, so that's permuting 3 out of n. What about permutation with repetition of r objects out of n? This is n to the r. Again, you can forget about all of these formulas if you want. And in each of these cases, you can use the fundamental counting principle. But actually, if the situation is so general, I prefer to use one of these formulas without drawing boxes and thinking about this, unless the situation is critical and you want to think about the cases. Thank you for this session.